Welcome to particle characterization. Question 1 from the problems at the end of Chapter 2 of Fundamentals of Particle Technology. So this is all about getting to learn particle characterization, and the problem starts with a microscope analysis where the results are shown on this table here. The two rows that are most relevant and pre-populated in their entirety are the rows that have the size range, or we sometimes call that size grade, in micrometers or microns, and you can see that they're at 5 microns there are no particles less than 5 microns. Between 5 and 7 microns, 50 particles, 7 to 10 microns, 150 particles, 10 to 15, 200, etc., until we get up to the larger than 50 micron range, when again we're back to no particles. So here are our two lines of data. That's a particle size range and then the number of particles in that particle size range. And then we're asked to calculate 3 other lines, to complete 3 other lines, and we've got some data already input just to start us off here. So what we'll be calculating then are the relative number, sometimes called the fractional number, although it's expressed as a decimal, the cumulative number undersize. Now this is an undersize and not an oversize, so we'll use the upper boundary of our size range, 7 microns in this case, so we're calculating the amount below 7 microns. And then this thing is a little bit more difficult to understand, the relative number per micron range. We'll come back to that in greater detail in a moment. So just a recap of what we're looking at the moment. Take the example of the size range 5 to 7 microns. In that size range we have 50 particles. So what's the relative number? Well, the first thing we need to do is to add up all our particles, and there's 50 there, that makes 200, that makes 400, 455, 500, 525. So this all sums to 525 particles. So that is essential information for calculating the relative number. We know we've got 525 particles in total. Okay, so clearly to calculate the relative number in this bottom size range, then we simply want the 50 particles that are in that range, and we need to divide by the 525 total number of particles, and that gives us the 0.0952 that we see illustrated here. So that's the number of particles in the range 5 to 7 microns. It follows then that that is also the number of particles, or the amount of particles of the full range less than 7 microns, because we have no particles below that range, so it's the bottom of the range. So that's the number fraction in that range, and it must be the number fraction up to the top grade boundary of that range. Let's just try the next one. So if we do the next one, we have 150 particles in the range. Again, we're dividing by 5 to 5, the total number of particles present, and 150, if I just get my calculator, 150 divided by 525 is 0.286, near enough 0.286. So the relative number here is 0.286. That's the relative number. The cumulative number is going to be the previous value, 0.0952 plus 0.286, which should give us, if we add 0.0952, should give us 0.381. So that's 0.381. 0.381. So that gives us the cumulative number undersize. So if you like, 38.1% of the distribution is less than 10 microns. 9.52% is less than 7 microns. That's just switching backwards and forwards between the decimal and the percentage. Okay, 38%. And I think you've got the idea. I mean, clearly we're dividing 200 by 525 to get the answer for that, 55 by 525 for that, 45 by 525, 20 by 525, and finally 5 by 525. And then for the actual cumulative values, we're just adding the relative number in the range to the previous value until we've summed all the way up. And clearly the cumulative number undersize less than 50 microns, less than that 50 microns there, is going to be 1. That's what we get, that's what we will get by adding those two together. It's obviously going to be 1 though. 100% of the distribution is less than 50 microns. Okay, good. The relative numbers should all sum up, of course, to 1. Okay, if you sum up that row. Okay, so that leaves us with just having a chat about a relative number per micron range. And before we do that, let me just clear a bit of space by moving this up. Okay, relative number per micron range. First of all, why do we do it? You know, what relevance does relative number per micron range have? Let me illustrate that with some random data, not the data that we've been looking at so far, but some random data. And supposing we have number of particles, so this is actual number of particles plotted against particle size. And we'll consider grades again. So if we have, let's have a grade looking something like that. Let's have a grade looking something like that. Another one looking like that. Now, supposing I was to say, where's the mode? The mode's the range with the greatest number of particles in, so clearly the mode looks superficially to be down here. Okay, but clearly that is not a fair comparison. It's not a fair comparison because we have a massive range in that particular grade and a very small range in this particular grade. So if we were to, let's say, normalize it by, instead of plotting number, we want number per micron range. Okay. Clearly we're dividing by quite a high value here because we've got a high micron range, and that would therefore give us a much lower number per micron range. If that was the micron range, if that was just a micron range, that stays unchanged, and as per the first one instance, wider range, that's obviously going to come down again. Okay, so now where is the mode? Well, the mode is, of course, now just there. So we've moved the mode from being apparently on the left to apparently somewhere in the middle. So if you like, that's a fairer comparison. There is that's one good reason for doing relative number per micron range. There is a more involved reason, a mathematically better reason, which if I just clear off some space, and that's to do with the functions. Sometimes we have discrete functions, which is what we have in this tabular data, and sometimes we have equations. And if we have equations, then we can get much more precise values for our answers, and presumably from that level of precision, a better understanding of what's going on and a better design of any process. So let me illustrate that. First of all, let's come back to this just here, the cumulative number undersize. So if we were to plot the cumulative number undersize, again, of no particular data, but our data would be fairly similar to this. It goes up to 1.0, starting from 0. If we take the example of our data-ish, I don't know whether this is a true representation of our data, but we'll just take the example of going up to 50 microns again. Our cumulative number undersize curve will look something like this. We're plotting against the upper grade boundaries in our table, and this is what we'll get. Okay. If we were to plot the previous two rows, the number and the relative number, then clearly what we would end up with are graphs that don't continually go up. They're graphs that will do something in the order of, if I join them up rather than make them into a histogram, do something like that. We'll have a certain range where there's a highest relative number of particles, or actual number of particles even. Now what I'm talking about in terms of a function is between these two here, because what we have here, the relative number per micron range, if that's what we're plotting here, the relative number per micron range, okay, against particle size, then we have, as that's number per micron range, and then that is the full micron range from x min to x max, 5 to 50 microns in our example here, then number per micron range over the full micron range, we've now got ourselves into a position where the integral of this function, let's call it little n naught x, okay, for number fraction, so the integral of little n naught x from x min to x max is going to be equal to 1. Sorry, I see I've just disappeared under me a little bit, but it's equal to unity, to 1. Okay, and that corresponds to what we're doing here on the cumulative curve. So if we were to integrate up to a arbitrary value, let's say 25 microns in the middle here, so if we were to integrate that up to 25 microns, you'd end up with that value for our cumulative curve, and that would be the 50% value, 0.5. Say. Okay, so the value we get on our cumulative curve is the integral from x minimum to wherever we're interested in on the x-axis. Okay, using x for particle diameter, of course. So wherever we're interested in, and if we're interested in the full distribution, integrating from x minimum to x maximum, then the integral is going to be equal to 1.0, the full range of the cumulative curve. So that gives us a very nice relation between the two. We called this little n naught x, lowercase n naught x, so let's call this one capital or uppercase n naught x. So our cumulative curve is uppercase n naught x, against x. Differential curve, or relative number per micron range curve, is little n naught x, and we can get between these quite nicely by integrating or differentiating. So if we wanted the function for the relative number per micron range, then it's going to be the differential of the cumulative curve function, whatever that is. So if we know a function for the cumulative curve, this one over here, the S-shaped curve that just goes up and up and up, so if we know a function for this one here, then we can differentiate it with respect to particle diameter. We're using the term x to represent particle diameter, and that gives us the equation for this differential curve, the relative number per micron range, just here. Why is that useful? Well, in other particle technology unit operations, we'll have equations for the design of processes, or operation, or simply the understanding of processes, where using the equation for number of particles, relative number per micron range, allows us to calculate pressure drops, velocities, flow rates, all those things that an engineer typically needs to calculate. So if we have a function, a mathematical function, that is a way we can make the mathematics simpler to solve. If we don't have that mathematical function, then don't forget we have a little bit of an analogy with summation. So I've got here a summation, but I've got here an integration, but of course we can sum particle numbers, and if we do that, number fractions rather, if we do that, then of course we'd expect to add, if there's number fractions that we're talking about here, they'd all sum up to 1. So there is this great, I don't think analogy is the right word, similarity between integration and summation, because of course integration is just summation on a very, very, very small basis. Okay, so that's a lot of words. What does it actually mean for completing our table just here? Okay, well let's complete the first one here. It's first thing, we're per micron range. So what's the micron range? Well, just here we're a micron range of 2, here a micron range of 3, here we're a micron range of 5, there's another 5, there's a micron range of 10, another micron range of 10 there, and the last one is also a micron range of 10. So if we're relative number per micron range, we need to take our relative number here, 0.0952, 0.0952, and divide by the micron range, which was 2, and if we do that, we get 0.0476. Likewise here, we're taking whatever we found the relative number to be, which was 0.381. The range here though is 3 microns, so we're dividing by 3 in order to get the relative number per micron range in there. Of course, when you sum these up, they won't sum up to 1. They sum up to 1 for the relative number, but here we've been dividing through each one of our grades by the range of that grade, so we're not going to sum up to 1. Okay, so that's how to do the problems. Let's see all the solutions in a spreadsheet, because obviously the sensible thing to do would be to solve this in a spreadsheet, and I'll say a little bit more. Here we go. So here is our spreadsheet, Let's see that I'm not in the way, so I can carry on. Okay, so here are the here's the left 5 microns, 0 number of particles, 5 to 7, just as we've been talking about previously, and here are our values that hopefully agree with what we said before. Number of particles in the size range 50, relative number 0.95, it's 3 significant figures. Cumulative is 0.95, and relative number per micron range, because we've got 2 microns, obviously that's the 4/8. So we just put the we've just done a spreadsheet. It's a very simple calculation to do in a spreadsheet for all these 3 rows. The totals are 525, totals of the relative number is 1, and then we have the figures, which are quite interesting. So let's have a look at the figures. Figure A to start with is the number of particles, and here is the shape of our curve when we plot against number of particles. Okay, what about relative number? Well, relative number goes up to or sums up to 1, but the relative number doesn't make any difference to the shape of the curve. All we're doing is dividing through by a constant, that constant being the total number of particles, 525. So, that's fairly straightforward. What about the cumulative number? So if we come down to the cumulative number, here is our cumulative number graph, and it starts at 5 microns, ends at 50 microns. 50 microns is 100% less than 50 microns, or 1 as a decimal, so it's that cumulative curve that we were expecting from my rough sketch a few moments ago. And then we have the last curve here is the per micron range curve. Okay, so it's not a cumulative curve, it's the number of particles per micron range between 5 and 50 microns. It looks a little bit like what we saw for the 2 curves above, but you'll see there is a significant difference because we're dividing by the per micron range, so we've sort of normalized it out. So it's the curve that goes up and down, the bell shape, the classic sort of bell-shaped curve. In fact, this curve here should be the differential of this curve. In other words, we have a small and positive gradient at the bottom here, which is the positive value there. We have a much higher positive gradient here, and then it comes back down to small positive gradient because we have a little bit of a tail at the top end, and you can see that's the case here. So this graph hasn't been differentiated from here. There's some differences that are obvious between the two. This graph is simply a plot of the relative number per micron range as per our discrete data in the table, which is why there's a slight difference to what we'd expect if we'd actually just differentiated, because this is based on the discrete data that we have rather than a continuous function that I was talking about previously. Okay, it illustrates the point. Oh, there is another interesting point on this graph. Remember I said that the area under this graph should equal 1, which is of course where that sums up to on the cumulative curve. The area under that curve doesn't look to be far off 1. Probably the best way of looking at that is to take the 0.02 there on the y-axis, and on the x-axis 50 microns, because 50 times 0.02 is 1. So we know an area of 1 is up from here and across there. And that looks about right, because that is the same area that if you were to steal this area and push it down, you'd end up with roughly the same sort of area. So we have an area of 1 underneath this curve, or pretty close to 1 anyway. So we're consistent with what was said a few moments ago. So I hope that explains what you need to do in order to complete this these rows in this table. more importantly, I hope it explains some of the background behind the calculations, why we're doing the calculations and what they show, and what to look out for in terms of the graphs that are formed. The next module, or the next question, is all about a mass distribution. This is all number distributions. These were particles that were counted on a microscope slide. A number distribution is fairly common, but a mass distribution, dealing with mass distribution, is even more common. So there's an importance to be able to convert the data you see here into a mass distribution, which is what we'll be doing in the next question. Okay, thank you.